So hi all, this is a bouncy ball. If you can see, the ball is bouncing off the floor. So let it complete. So this simulation is more of an Excel challenge rather than a physics challenge. So what's the physics here? The physics is a ball that bounces off the floor. So that is thrown into the air where the air resistance is 0. Now it moves under the influence of gravity and it falls on the floor, and every time it hits the floor it loses a part of its momentum. So if you can see, so the first trajectory, the first hop that it makes will be that of a parabolic motion. Then it bounces off the floor and it drops its momentum by a percentage. Then again it follows another parabolic motion. So it goes on and on and on till it drops down, or it drops dead. So now if we make the angle 90 degrees, we'll see how it goes. It goes up. This is out of the chat. Comes down, loses a part of its momentum, goes up, comes down, again loses a part of its momentum, and drops. So if you see, I have taken some initial parameters like the initial velocity, the velocity at which it is thrown into the air, then angle. Here is the angle. I've taken 90 degrees. Then this is the gravitational pull, the gravitational acceleration, which is 9.8 meters per second square. This is that of Earth, and this damp, a 0.06, is a dampening factor. That means I can choose to make the floor, in a sense, more elastic, or make the ball more elastic, where it will bounce off, losing a very less part of its energy. So if I make it 0.9, that means it will lose its momentum by only 10%. If I make it 1, that means it doesn't lose its momentum at all. So let's see, let me move it with an angle 30 degrees. Let's see. Here what we have said is it is 1, that it doesn't lose any energy. Let's see how it goes. So it will go with identical parabolas. It will not lose any of its energy. It will just go on and on and on like this. Just pause here. So what's the challenge in Excel? So this is physics. We just talked about physics. That when it bounces, bounces off the floor, it loses a part of its momentum. And in this last example, what we said is we set the dampening factor at 1. That means it doesn't lose any of its energy. Now the challenge in Excel is to find an equation of the trajectory that will plot all the hops at one go, which will enable me to change the initial parameters such as the velocity, the angle, the gravitational pull, that is g, the acceleration, and then the bounce. So these are the initial parameters that I can change, and it will plot the locus, and I don't have to tweak the equation in between for each and every hops. So that's a challenge in Excel, because the equation has to be a seamless one. It has to understand that it has already hit the floor, then it is again going up with a velocity v, which is a factor of the initial vector velocity. Why it is a factor? Because we're saying there is a dampening factor. Whenever it hits the floor, it loses a part of its momentum. Now let's try out different angles or different parameters. So it's 50. Here goes 50. This is 98, and the dampening is 0.8. Let's try this out. Let's start it from the beginning. Let's make it 0.6 then. That means it will die out faster. Let's make the gravitational pull a bit harder. Let's say it's on a bigger planet where the gravitational pull is almost twice that of Earth. So let's make it 20. So it should move faster. Let's see. Let's make the angle 90 degrees. So Microsoft Excel is an excellent tool that empowers us to push the envelope to try out various simulations. So we can try out different equations and we can plot it on the charts. We can have this a little simulation that verifies that the equation is following the correct locus, and we can check our theories here. So let's try out something funny. Let me change the dampening factor to 1.3. So the velocity is 20, the initial angle is 50, and the gravitational pull is 9.8. Let's see how it happens. Here you go. So a smaller trajectory, then a bigger one, then another bigger one. This actually defeats the law of conservation of energy, because what happens here is every time it falls on the floor, it gains momentum. So in this simulation, we do not have any restriction for the laws of conservation of energy. However, that applies. That doesn't apply in this example though. So that means the dampening factor cannot be greater than 1. When it is greater than 1, what it means is every time it hits the floor, it gains energy. That doesn't happen in the real life. So let's make it 0.5. And here it goes. Let's let's make it 90 degrees, and this 40. See how the bounce happens. Thank you so much.